Today we're going to start talking about hydraulic fracturing. We already started talking about hydraulic fracturing, but we're going to talk more specifically first about hydraulic fractures in nature very quickly. Then we'll talk about how hydraulic fractures are important in well testing. And then we'll go to hydraulic fracture design. Before I forget, I'd like to encourage you to attend tomorrow's seminar from Scott Sheffield, CEO Pioneer. It's going to talk about the importance of unconventionals in the US for the last 20 years, and also what is the outlook in the future. I was talking today to him this morning, and he thinks that we have just tapped a very small part of the resources in the Permian Basin, and there is still a lot more to be produced thanks to hydraulic fracturing. So let's start then with hydraulic fractures. First of all, I wanted to emphasize that hydraulic fracture is not something that it's done just by petroleum industry. It happens naturally. And the evidence of that is what are called dikes, which are intrusions of either magma or sedimentary rocks like sand or like gravel into formations. The difference maybe that could be in natural formation is that the source of pressure comes from pressurized formations underneath the fracture formation, and as those formations reach a pressure high enough so that they overcome the minimum principal stress, they literally open the earth in two, and those fluids go up, and those are what we call dikes. And if the minimum principal stress is horizontal, they grow vertically. If at some places the minimum principal stress is vertical, they extend laterally. And in the case of magma, if it solidifies after some time, this is what you see. This is the result. So this is, for example, a natural hydraulic fracture of a magmatic intrusion that you can see how it grows up in this direction. So in this case, the horizontal fracture, what do you think it is? It is horizontal, it is vertical. So the hydraulic, I was getting distracted by some other people distracting me. So let me say this again. What the hydraulic fracture is vertical, right? In this case, what is the direction of the minimum principal stress? It's horizontal, right? In this place, the minimum principal stress was horizontal, so the hydraulic fracture is vertical. There are some examples of these dikes, magmatic dikes, in I think this one is in New Mexico, a place called Shiprock, in which you can see how this sort of it looks like a steep wall, but it's actually, let me dim a little bit the lights. They look like vertical walls and are actually dikes, magmatic dikes that grow up with horizontal stress in this direction, and that's why they grow vertical. There are some other examples of dikes that are also caused by intrusions of sedimentary rocks. Sometimes when you have a sand that has a pore pressure that is so high that the effective stress becomes zero, it just moves like quicksand. and that quicksand sometimes can also go up and intrude into upper formations and form dikes, but these are not magmatic, these are made of sand. So there are large dikes like these in several parts of the world, and sometimes they are also used to tell you what is the orientation of hydraulic fractures and what is the orientation of the minimum principal stress in some places in the world. Yes, there was Shiprock, New Mexico. I think if you guys watch one of the Transformers movie, I think one of the places they go is a place over here. I don't remember which one. I didn't see. I started watching those movies, but I could never end those movies because they were pretty bad. Okay, so let's move now to hydraulic fractures that we do for well testing. And for those, there are going to be 3 types. So today we'll try to cover the first 3 types. And hydraulic fractures are very useful for, we already know they are useful for letting us know what is the minimum principal stress. That is very useful for drilling stability, for fault reactivation, and also for hydraulic fracture design. But we're going to see later on also that some of these tests are very useful also for injecting safely fluids like brine or gas or CO2 or anything you may inject in a formation. Okay, so we're going to start with the first one, which is the leak-off test. The leak-off test is a test that involves hydraulic fracturing, and it's mostly done when you're drilling. And because it is done when you're drilling, it uses drilling mud. We're going to see that there are several ways of causing a hydraulic fracture. You can do it with drilling mud, you can do it with fracturing fluid, or you can even do it with natural gas or nitrogen or anything. So it's very important to recognize what type of fluid you're using to predict correctly what's going on with a hydraulic fracture. So in the leak-off test, basically, what you do is you get to a point in which you case a wellbore, and then after you case it, you may want to cement it, and then you may isolate that zone and pressurize it with drilling fluid so that you get to know what is the maximum pressure that you can achieve at this location. Usually that maximum pressure, if you remember what we have seen for wellbore stability, that will give us our upper bound, how high in pressure you can go so that the wellbore does not fracture. We learned the equations that allows us to calculate that, and we're going to use those equations now. But if you really want to know the actual value, the only way to do that is to perform a leak-off test, increase the pressure, and see what is the maximum value. Okay, all right, so we're going to do that. But before we do that, let me see. Well, let me first assume some conditions, so I'm able to draw what I'm going to draw. We're going to assume for this example that we are under normal faulting. So we know this is true. And I'm going to assume something else, which is going to make it a little bit easier what I'm going to plot next. I'm going to assume that there is very little stress anisotropy in the horizontal plane, and also that I'm dealing with a vertical wellbore. All right, so we use the Kirsch equations to calculate what was the maximum breakdown pressure. That is the maximum pressure that you can have in your wellbore so that it does not fracture. And that equation was like this. This is something that we knew from before, okay? So nothing new so far. Minus sigma H max plus the tensile strength, and I'm going to ignore the thermal effects. We are saying that now these two are about the same, right? So from here, I just have 1 sigma H, and those are the same. So this is going to be 3 sigma H minus sigma H. It's just going to be 1 sigma H. So this is going to be 2 sigma H plus the tensile strength. This is what Kirsch will tell me that will be the maximum pressure that the wellbore can take. All right, so let's see how that would affect the pressure response in a wellbore when I inject a fluid. So I'm going to draw here the injection rate as a function of time, and I'm going to have cycles. At the beginning, the injection rate is going to be 0, and then increase quickly, and then I'm going to maintain it constant, and then I'm going to stop it, and then increase it again. And my objective is to predict what will be the pressure here inside the wellbore. Notice that now we have put some packers in here so that now this is a closed volume, and the pressure in the wellbore is not going to be only a function of the density of the mud. Probably that's going to be the initial value, but it's also of course going to be a function of the depth, but also it's going to be now a function of the injection rate. Because this is more or less a closed volume, we have drilling mud that makes here a mud cake. So the drilling mud is not going to get so easily into the formation. So if you keep on injecting, what do you think is going to happen with the pressure? So let's say that before we inject, our pressure is, well, let me start by putting some very important values in here. First, we're going to have the pore pressure. And I'm going to set this density of the mud so that the pressure at the beginning is barely above the pore pressure. Okay, so if I start injecting, and this is more or less a closed volume, what's going to happen with the pressure? It will go up, right? So I agree with that. It will go up. But now my question is, will it go up forever? Can it go infinitely high? No. And what is going to be the maximum value of the pressure that you can get to? It's going to be PB, breakdown pressure, and I heard something else? Well, I wrote this equation because I wanted to show the influence of stress anisotropy, which in this case there is no anisotropy, and of tensile strength. So look, the PV here, according to this equation, is going to be, of course, higher than the pore pressure, and then it's going to be 2 times the effective horizontal stress above the pore pressure plus the tensile strength. So let me assume that more or less this is 1 sigma h, this is 2 sigma h, and this is the value of tensile strength. Well, according to this equation, the maximum pressure you can get to is going to be limited by this value, that is the value of PV, right? So pressure is going to go up, and then it's going to reach a peak, and when it reaches a peak, and if you keep on injecting, notice that here injection rate is still constant. What do you think is going to happen at that point? We're saying it's reaching a peak, right? Because it cannot go further. But what is going to happen after that? Will it go down? Will it stay constant? Why will it drop? And so? Any other suggestions? Why would it drop? You don't have the tensile strength anymore, right? So that's one of the. We're going to see that very clearly in just a bit. But there is one more thing. If you're pressurizing something that is more or less closed, and you suddenly break it, probably you will have a lot of strain energy that accumulated when it was deforming, and when it breaks and you open a fracture, all the fluid that was pressurized, and if that volume increases quickly, the pressure should go down, right? Because that was very well confined, and now it broke. You expect the pressure to go down, and the pressure actually goes down. But now the question is, how much does it go down? And what is that equilibrium? Stress or pressure? I agree that cannot go lower than pore pressure, but at this point you're still injecting, you're still pumping fluid, so the fracture is open and it is propagating. So what is the maximum or the minimum value that it can get to? I heard pore pressure. Notice something else. What is pore pressure plus sigma h? SH, or if this were to be the minimum principal stress, we could think that that's S3, okay? Which in this case it is, because both of them are the same. So if the fracture is propagating, do you think the pore pressure is going to go lower than the minimum principal stress? Probably not, right? But not probably. Very, for sure, no. Because if the fracture is open, in order to be open, it has to be larger than the minimum principal stress. But since the fracture is still propagating, what we're going to get to here, it's a value which is not quite the minimum principal stress, but it's a little bit more. And how much more? That depends on many factors, like the viscosity of the fluid, the properties of the rock, and a few more things. And we're going to call that pressure, that additional pressure that you need for a fracture to propagate on top of the minimum principal stress, the net pressure. So the net pressure is going to be the difference between the pressure in the fracture minus the minimum principal stress, which in this case is SH. It needs a higher pressure in order to propagate, otherwise it won't. It might, but at a very, very small rate. Okay, so before we move on, let me tell you a few things. Sometimes, you know, when this point, or this curve starts to bend, some people call this the leak-off point, and some people also argue that that's a point in which you have the starting fracture. It's an important point to recognize, because sometimes you may not want to go all the way on fracturing your wellbore, especially if it's a very expensive wellbore. Probably if you know that you're getting to the point which is going to fracture, you might just stop there. That's what is called a short leak-off test, because you don't go all the way into this region. You know that it's about to fracture, so you stop it and you say, okay, I'm pretty sure that I'm gonna just go up to this pressure next time. In the wellbore, when I continue drilling, I'm not gonna pass that value. This point over here, the maximum is called the breakdown pressure, and that's why we called that value before PB. And the pressure at which the fracture propagates, and this is more or less a constant value. Sometimes it may, if the fracture gets a lot longer, it may go down or it may go up, but for relatively short fracture is about constant, and this is the fracture propagation pressure. And up to now, we're good. All right, so yes, Mr. Wheeler, you have a question.
So are these fractures, are they instantaneous? So like if you apply like a pressure, right? So when it's breakdown pressure, is it like instantaneously going to formation and creating fractures at that point? Or is it like, does it take like 30 seconds before it to like fully start forming fractures? Or
The fractures are going to form at the velocity at which you are pumping a fluid. Because, for example, if you were to fracture a solid in vacuum, or if you were to fracture the screen of your cell phone, you can have those fractures open and they can propagate very quickly, okay? But in the subsurface, you cannot have a fracture open without something inside. And so, in the subsurface, in order to have fractures open, you need a fluid inside. And in order to have a fluid inside, you need to pump it in. So the fracture is just going to open at the velocity at which you're injecting your fluid. Sometimes, if you get into very specific concepts, some people think that at the tip of the fracture there is sort of a vacuum, or there is no fracturing fluid, but it's just a very small region. Yeah. You have a question? Time. This time. Yeah.
For the leak-off point, is that when it deviates from being a straight line?
Yeah. Yes. Okay, so we got to this point, and now we shut in the pumps. What's going to happen with the pressure? It will go down, right? Because you're stopping pumping, so the pressure has to go down. Why? Because some of the fluid, actually now we can go ahead and at this point you have a wellbore and you have a full-grown fracture, and you were pumping at this point, and some of the fluid was also leaking into the formation through the fractures. So whenever you shut in the pumps, even though you're going to kill this fluid from the wellbore through the fractures, still the fracture is going to leak off from the wellbore and from the fractures into the formation, so the pressure is going to go down. Now the question is again, how much or how low is the pressure going to go?
Pore pressure.
Second?
Pore pressure.
Pore pressure? Well, if you were just not controlling the pressure in the wellbore, if you just stop it, very likely yes. Now this time it will go to the value of the pore pressure, and the pressure will go down quickly at the beginning, and then it will start to go down slowly, and it will take some time to get to the pore pressure. Maybe it will never reach the pore pressure, or well, in an infinitely long time it will reach the pore pressure, but in a short time it might not. But it's not going to go below the pore pressure. There are two very important points or times to consider over here. The first one is right after you shut in the pumps, there is going to be a pressure which is called the instantaneous shut-in pressure. The instantaneous shut-in pressure is a pressure, the highest pressure right after you shut in the pumps, that starts to show a gradual decay of pressure. Okay, I'm going to show some images, and in my notes I have some nice examples that will show that much clearer than this one. But it is somewhere right here. Okay, you shut in the pumps, pressure goes down very quickly, and then it starts to go down slowly. Well, the maximum point is the shut-in pressure. And after some time, after you shut in the pumps, the fracture is going to still be open, right? You're going to be here. Let me just draw half of this fracture. So this is the wellbore, and this is the fracture. At the shut-in time, there is no more fluid from the wellbore into the fracture, but the fracture is open and still leaking. Well, there is going to be a point in which this fracture is going to close, because all the fracturing fluid is going to leak into the formation, right? And that's going to be at what is called the fracture closure pressure, FCP. And that fracture closure pressure is going to be very, very close to the minimum principal stress. Mr. Wheeler, you have a question?
Yeah, so what about proppant? So if you put proppant in there, is that going to keep the fracture open even though you're not pumping, or will it close anyway? Just like small grain particles?
It will keep it open, but with solids inside. In this case, you're keeping it open just with fluids. And when those fluids get into the formation, the fracture is going to close. Probably you will leave behind your mud cake that now is going to be there in the fracture, but there is going to be contact solid to solid again, rock to rock again.
Okay, so there's no proppant in this case.
In this case, there is no problem because we're doing a leak-off test with drilling mud. We're going to get to the proppant later on, okay? So at the point that the fracture closes, that's going to be the fracture closure pressure. And if you can identify that fracture closure pressure, that's going to allow you to link the fracture closure pressure with the minimum principal stress. And that's how you can measure the minimum principal stress from this leak-off test. It's not with this point, it's not with that point, is not with the fracture propagation pressure, because we know that's higher than minimum principal stress, is with the fracture closure pressure. I'm going to show an example in a sec. At the point of the fracture closure pressure, let me do a schematic here. You have a wellbore, you have a fracture, but now that fracture is closed. And the pressure is still going to go down because you still have some leak off from the wellbore into the formation, but almost nothing from the fracture into the formation. I'll come back to this and how to recognize this fracture closure pressure. But before we do that, let's see what's going to happen now if we inject again a drilling mud. What's going to happen with the pressure? It's going to go up again, right? How far is it going to go up? A little bit low PV, and how can you be a little bit more specific? Can we account with the tensile strength of the rock? No, because it was already fractured, right? Because it was already fractured, now our PV is a different one. It's not the same the same that we had before. And it actually is going to be lower, but notice that it's still higher than the minimum principal stress. And then when it goes into the far field, it goes again into the fracture propagation pressure, which is about the same as before. And if you were to shut it in, it will do the same as we saw before. But now the PV is going to be different, because now you are extending a fracture in a formation which is already fractured. Mr. Wheeler.
So, after the fracture closes, what's making the pressure go down? Is there still a little bit?
Here? So notice that the pressure at this point is much higher than the pore pressure. So still the fluid is going to try to get in to equilibrate with the pore pressure. So that's why it's still going down. Yes, Mr. Barrera.
Will the leak-offs be less significant after the first closure? Like, because you're having fluid outside the wellbore, right? Or does it?
For the second one?
Yeah.
Well, probably if you think that your mud cake is already there, yeah, you could say that leak-offs will be less significant.
But doesn't. Would it affect? I'm trying to understand the slope, because you said there's a slight change.
This slope?
Yeah, to understand the.
Well, no, I meant it to be more or less the same.
Oh.
Okay? And probably, as you say, probably will take a little bit more of time actually to close and to reach the initial value. The important thing about this exercise is to notice that sometimes you have to go over the hump in order to get to the fracture propagation pressure. And that depends on the tensile strength of the rock, but also depends on the stress anisotropy. This is the most unfavorable case in which you have to increase a lot the pressure to go into the fracture propagation pressure. If you were to start with a high stress anisotropy, if you started with a large difference between these two, notice that sometimes, for example, if sigma h mean were to be 1/3 of sigma h max, as it is more or less in a strike slip regime, this will cancel. And if this one cancels, everything you have in the breakdown pressure is the tensile strength. So if this one goes over a hump or it goes directly into the fracture propagation pressure, depends a lot on that stress anisotropy. So let me show you that case of fracture or closure pressure, because you're gonna have to solve a problem related to that. And this is the same thing that I just showed before, and this is the example that I was mentioning. So this is a real injection test. You have the rate in red and the pressure in blue, okay? So in this case, they start to inject, they reach more or less a constant rate, and you see that they reach right away the fracture propagation pressure. After you stop injecting, the pressure goes down very quickly, and making a zoom on that data over here, you can pick up the instantaneous shut-in pressure as the largest pressure after you have a gradual decay in the data. It will be the first point in which the pressure exhibits a gradual decay in the data. This is sometimes a little bit subjective, okay? But once you replot your data, you will see a lot more easily which one is this instantaneous shut-in pressure. Why do we need this shut-in pressure? Because in order to calculate the fracture closure pressure, what you're going to do is you're going to plot the surface pressure as a function of the square root of time after the instantaneous shut-in. When you do that, this is the same data. I'm starting to pick up the data from here to after time. When you plot that data as a function of the square root of time after the shut-in time, so at the shut-in time that would be 0, you see that when the fracture is open, the pressure goes down linearly with the square root of time, and that's telling you the fracture is still open. That's telling you that the fluid is leaking from something that has sort of a planar geometry. In which case, in this one or in this one, you think the pressure is going to go down more quickly? With the fracture open or with the fracture closed? Why? Because there is more surface to leak, right? And it happens that with this geometry, that pressure is going to go down linearly with the square root of time, but when the fracture closes, it gets more gets to a more gradual decay of the pressure, and it gets slower, and the pressure now, it doesn't go down so quickly, and it doesn't go down linearly with the square root of time. At the point at which you find that deviation, that's a fracture closure pressure. So I'm still uploading the website to put that question in there, but hopefully it's going to be there by Wednesday. And you will see that you'll have to solve a very similar example of this. So doing the leak-off test then is very useful for knowing what is the maximum pressure that you can utilize in the wellbore in order not to fracture it, and also to calculate the minimum principal stress that you can use later to do drilling stability calculations or fault stability or some others that you may be interested in. But remember, the leak-off test, it's done by drillers for drilling mostly. Let's see the second type of test, which is very similar to this one. And this one is called the DFIT test, and that stands for Diagnostics, Fracture initiation test, and some other times also goes by the name of the mini-frac test. Well, it is exactly the same principle as the one before, but with the difference that now this is not done for drilling. This is done for completion, and probably many times it will be done after you do a perforation through casing, and the principal objective of this mini-frac test is to determine what are going to be the fracturing pressures for a completion job. So this is not for drilling, this is for completion. And if you are doing completion, what kind of fluid are you going to use? Are you going to use drilling mud now? What are you going to use? You're going to use fracturing fluid, right? So it's a very similar concept. You close a particular region, pressurize it, measure the maximum pressure, measure the fracture propagation pressure, and then stop injecting, and with that, then later you can calculate what is the minimum principal stress. And if you use some special methods, you can also predict what is the permeability of the formation, something that it's very important for unconventionals. So here you use a fracturing fluid. Usually you also use small volumes, like less than, well, more or less 10 barrels or so. And usually you will go with small injection rates too, more or less than 3 barrels per minute. But it is exactly the same. Again, if you plot the pressure in this case, let's call it the pressure in the fracture, it will go up. Very likely it will go over a peak, and then it will go into a fracture propagation pressure, and once you shut in the pumps, it will go down very quickly, and then it will go down. I'm not going to go into details of this type of analysis of this data, because actually some companies have different methods to analyze it. So if I show you one method, probably that same method is not utilized by all companies. So it doesn't make too much sense to go over all of those. What I'm going to tell you though is that the analysis is very similar to the one we saw before, with this trying to recognize what type of fluid behavior you have, either if you have leak off from a fracture or leak off from a wellbore. And what it's used currently in industry is replotting the data with something which is called a G function. And a G function, what it does is something very similar to the square root method. It just tries to predict the flow by converting time in a time which is, it will give you more or less a linear relationship of pressure with time if you had a planar fracture. So basically it's just replotting this data, as you can see over here, and finding an inflection in this curve of the G function, similar to the square root method but a little bit more advanced, And from there you can calculate what is your minimum principal stress. But it is very similar. And if you are interested, you can check this paper in here. But the most important thing is to remember that this diagnostic fracture injection initiation test is for hydraulic fracturing. There is one more method I'd like to talk about that is also involves a hydraulic fracture, but it's quite different from the ones that we have seen so far. And that one is the step rate test. In the step rate test, what you want to do is you want to find what is the maximum injection pressure for not fracturing a wellbore. Okay? So in this problem we want to inject fluids. It's not for drilling, it's not for completions, because completions you inject fluids but for a short period of time to make a fracture, but then you're not injecting anymore. In this case, we're doing continuous injection. And you want to find what is the maximum injection pressure so that you do not cause a fracture. Can you give me examples of what you may inject continuously? What? What kind of fluids? You can tell me why too. What kind of water? Like fracturing water or wastewater. All that you want to get rid of, and some other fluids we're going to talk about on Wednesday. Okay. So I'm going to try to get your grades by Friday. Hopefully we can talk about that at the end of the week. What?
Do we have lab?
No lab this week.